Hello students, in today's lecture we are going to learn about mechanical properties of solids. NCERT section 8.1, 8.2 and 8.3. This is disclaimer, strategy for competitive exams. So first, master definitions and formulas for all types of stress and strain. After that, you need to learn Hooke's law using Young's shear and bulk moduli with negative sign convention. Analyze stress strain curves. These curves helps us identify key points like the elastic limit, yield strength, ultimate tensile strength, and differentiate between ductile and brittle materials. Recall the SI units and dimensional formulas. Stress and elastic moduli are measured in pascals or newtons per square meter with a dimensional formula of m L, L inverse T raised to the power minus 2. Calculate elastic potential energy, density, and total potential energy. Practice some numerical problems by linking theory to real world applications, such as estimating the height of a mountain. Solve problems from past year JEE and NEET papers. Recommended books. Visit our website to get the suggestions of the books and guidance. These resources will support you learning journey and provide deeper insights into the mechanical properties of solids. Learning objectives. By the end of this lecture, you will be able to understand the uh, concepts of mechanical properties of solids and concepts of stress, strain, and Hooke's law. All right. So in today's lecture, we will cover first 8.1 introduction. After that, 8.2 stress and strain. Then we will discuss Hooke's law. All right. So we will start by understanding uh, what makes a solid unique. This is basic introduction. So the particles in a solid are held together by strong forces. This is why solids maintain their shape and size under normal conditions. Look at figure. This is the constituents of the solids are bound by strong forces, or we can say crystalline solid have a highly ordered structure, which a result of the strong forces binding their constituents. This order lines is what gives crystalline solids their distinct properties such as sharp melting points and clear geometric shape. Next, deformation. Basically, deformation occurs when an external force is applied to a solid, causing a change in its shape or size. This concept is important in understanding how materials respond to forces, which is important in fields like engineering and material science. If a solid returns to its original shape after the force is removed, we call this elastic deformation. This property is essential for materials that need to absorb energy and then return to their original form, like rubber bands or springs. Elastic deformation is a key concept in designing materials that can withstand stress and strain. Now, we are focusing on fundamental concepts in physics, elasticity. This is a key property that helps us understand how materials behave under force. So, to discuss about elasticity, if we talk about the elasticity, we can say the property of a body by virtue of which it tends to regain its original size and shape after the applied force is removed. This is important because it determines how materials can be used in various applications, from construction to manufacturing. Alright, suppose we have a uh, elastic material. If we applied some force on that material, it will be and the size and shape will be changed. But after removing the force, the shape will regain its original condition. So this is the phenomenon of elasticity. Materials that show elasticity and can easily return to their original shape after being stretched or compressed are called elastic materials. Think of a rubber band or a spring. They both return to their original form after being uh, deformed. Examples: rubber bands. All right. Next, we have plasticity. This property refers to a material's ability to not regain its original size and shape after the force causing the change is removed. If we talk about definition, so we can say it's the property of a body to not regain its original size and shape even after the force that changed it is removed. Materials that exhibit a plasticity can be easily shaped or molded are known as plastic materials. Examples are clay or putty. Alright. Now, elastic behavior of solids. In solids, atoms and molecules are arranged in a stable equilibrium. This means each particle is balanced by forces from its neighbors. Look at figure. Here it shows a spring wall model. This model helps us visualize how atoms are connected by interatomic forces represented by springs. So here springs are interconnected. Spring ball uh, model. This is a microscopic model that helps us understand the elastic behavior of solids. It's a simple and powerful way to visualize how materials respond to forces at the atomic level. Atoms are imagined as balls. This analogy helps us see how each atom is like a small sphere that can move slightly when a force is applied. Interatomic forces are represented by springs. These springs illustrate how atoms are connected and how they can stretch or compress when forces are applied. All right. Now, uh, elastic behavior of solids. When an external force is applied, the atoms are displaced from their equilibrium positions. and the intra-atomic distances change. Alright, this is important because it affects the material's ability to return to its original shape or form. The atoms are not just moving randomly, they are being pushed out of their usual position. Alright, so this force here, the displacement here, this displacement creates a restoring force in the springs, interatomic forces that drives the atoms back to their original positions. It's the restoring force that allows materials to regain their shape once the external force is removed. Think of it like a rubber band snapping back after being stretched. If the external force is removed, the interatomic forces work to restore the original size and shape of the body. This is the essence of elastic behavior. It's a fascinating how materials can remember their original form and return to it, which is why elasticity is so important in material science. Elastic behavior of materials is important in engineering design. In all right, examples. When designing a building, engineers must consider the elastic properties of materials like steel and concrete. These materials need to be able to handle stress and return to their original shape to ensure the building's integrity. The same principles applies to design of bridges, automobiles, and ropeways. Each of these structures may be able to withstand various forces while maintaining their shape and function. Understanding elasticity is a key to designing these everyday structures safely and effectively. Now, uh, we are going to explore the concept of stress in the context of mechanical properties of solids. So, first, we have stress. Definition of stress. Stress is essentially the restoring force per unit area. This means that when a force is applied to a material, the material develops an internal force to resist the deformation. This internal force is what we refer to as stress. When a deforming force Fd is applied uh, to a body, internal restoring forces Fr are developed. Alright, here look at figure. So here Fr are the internal restoring force. Fd is uh, deforming force and Fr is the internal restoring forces. So the materials responds to by developing internal restoring forces denoted by Fr. Look at figure. These forces act within the material. This visual helps us understand the behavior of stress in solids. In a state of static equilibrium, the internal restoring force is equal in magnitude and opposite in direction to the external deforming force. This balance is important for maintaining the shape and structure of the material. Understanding this equilibrium helps us predict how materials will behave under different forces. So, mathematically, stress is equal to force upon area. Magnitude of stress is the magnitude of the applied force F divided by the area of the cross section A. This relationship shows us that stress increase with greater force or smaller area, which is important for understanding material strength. SI units Newton per meter square or Pascal. Dimensional formula M L inverse T raised to the power minus 2. So, types of stress. There are three types of stress. First, longitudinal stress. This occurs when a force is applied along the length of an object, causing it to stretch or compress. Think of pulling or pushing a string as an example. Second, shearing stress. This type of stress happens when forces are applied parallel to the surface of material, causing it to slide over itself. Imagine layers of a deck of cards sliding past each other. And third, hydraulic stress. All right. So we will discuss each stress one by one. So first, uh, we will learn longitudinal stress. So when a solid object is subjected to an external force, its size or shape can change in three different ways. See figure 8.1. First, we have a tensile stress, which elongates a cylindrical body. Next, shearing stress deforms a cylinder by an angle theta. And third, hydraulic stress occurs when a solid is under stress normal to its surface. Each type of stress affects the material differently, and understanding these differences is important to predicting materials behavior under various conditions. So, longitudinal stress. Let's start with longitudinal stress. So, when a cylinder is pulled by two equal forces on opposite sides, the force per unit area resisting the pull is known as tensile stress. Imagine a pulling on a rubber band. The resistance you feel is similar to tensile stress. Look at figure showing a cylindrical body under tensile stress, which elongates by a certain amount. Initial length L, and after the stress, the L plus delta. In this case of tensile stress, the deforming force is applied normal or perpendicular to the cross section of the material. This is a key point because it helps us understand how the materials will deform under such forces. If the cylinder is pushed in by applied forces, the force per unit area resisting the push is called compressive stress, like squeezing a sponge. The materials resist the force trying to compress it. Tensile or compressive stress are also called as longitudinal stress. Now, second is shearing stress. Let's discuss shearing stress. This type of stress occurs when two equal forces are applied in opposite directions, parallel to the surface of a material. So, when two equal forces are applied in opposite directions parallel to a cylinder's surface, each face moves in opposite directions. Look at figure 8.1. We see here a cylinder experiencing shearing stress. The force is causing each face of the cylinder to move in opposite directions. And this one, backward and forward direction. This is forward direction, this is backward direction. This visuals helps us understand how the materials deforms by an angle theta. All right. In this case, deforming force is applied tangentially, parallel to the cross-sectional area of the material. This is important because it differentiates shearing stress from other types of stress, like a tensile or compressive stress, which is act perpendicular to the surface. This movement causes a force that tries to restore the cylinder to its original shape. This force attempts to return the cylinder to its original shape, highlighting the material's elasticity. The concept is fundamental in understanding how materials respond in different stress. So, let's continue with shearing stress. Force per unit area resulting from the applied sideway force is called shearing or tens- tangential stress. This means that the stress is distributed over the area where the force is applied. Example of shearing stress can be visualized when a book is pressed with the hand and pushed horizontally. This action creates a shearing effect similar to what is shown in figure 8.1c. This example helps us see how shearing stress works in real life situations. Alright, now third is hydraulic stress. This type of stress occurs when a solid is submerged in fluid and experiences pressure from all directions. It's important because it helps us understand how materials behave under fluid pressure. So, sphere experiences uniform compression from all sides by the fluid. This is a visual representation of hydraulic stress. The fluid applies pressure evenly across the surface of the sphere from all directions. Look at here, from all directions. So, uh, here, figure 8.1d, this one depicts a solid sphere placed in a fluid that is under high pressure because the pressure acted on in from all directions on the object. Fluid applies a force which acts perpendicular on each point of the surface sphere. This process is called hydraulic compression. Alright, I hope this is clear. Now, uh, this reduces the sphere's volume without altering its shape. So, this is important because it shows how the materials respond to a uniform pressure from all directions. A common scenarios includes the sphere develops internal forces that counteract the applied forces from the fluid. These internal forces are important because they help maintain the integrity of the materials under stress. When removed from uh, Once the sphere is removed from the fluid, these internal restoring force work to return to its original size and shape. This demonstrates that the material's ability to recover from deformation, which is an essential property of solids. Internal restoring force per unit area is termed uh, hydraulic stress and is equal in magnitude to the hydraulic pressure applied force per unit area. Now, we are going to explore the concept of strain. Let's examine first strain. Strain is a measure of deformation or change in shape that occurs when a material is subjected to an external force. This means that when you apply a force to an object, strain tells us how much the object changes in response to that force. So this tells how much an object gets deformed compared to its original size or shape. This comparison is important because it allows us to quantify how much an object has been deformed relative to its initial state. Strain is a dimensionless quantity, meaning it has no unit. Mathematically, strain is equal to change in configuration divided by original configuration. And this topic is a very important from an exam point of view. So there are three types of strain. First, longitudinal strain. Second, shearing strain. Third, hydraulic strain. We will discuss these three types of strain one by one. All right. So uh, let's start by identifying the types of strain. Strain can be categorized based on how forces are applied and how the materials deforms. So here uh, we know already strain can be categorized into different types of based on nature of the applied force and resulting deformation. The first, longitudinal strain. Longitudinal strain occurs when a material changes its length due to applied force. It's important to recognize this type of strain because it directly affects the dimensions of objects. So when a cylinder is pulled or pushed by two equal forces on opposite sides, there is a change in length of the cylinder. This is a classic case of a longitudinal strain. The figure here shows how the cylinder elongates by a certain amount delta L under tensile stress. Look at here, the forces are applied uh, and the resulting deformation. The forces are first one vertically downward and vertically. Now, uh, strain can be categorized into different types of based on nature of the applied force and resulting deformation. So first, longitudinal stress strain. The ratio of this change in length delta L to the cylinder's original length L is referred to as longitudinal strain. Delta L, longitudinal strain is equal to delta L by L. This is expressed here mathematically. Now, shearing strain. So let's focus on shearing strain. Now, shearing strain occurs when a force causes one layer of a material to slide over another. This is a different from stretching or compressing because it involves a sideways shift. So if we talk about the definition, so we can say shearing strain is defined as the ratio of the relative displacement of the four faces delta x to the length of the cylinder L. This concept illustrated in figure 8.1b, where you can see how the cylinder deforms by an angle theta. So look at here, deformed by angle theta, and forces are applied opposite. So shearing strain is equal to delta x upon L is equal to tan theta. In this equation, theta represents the angular displacement from the vertical. This relationship helps us quantify how much a material has been sheared. Now, shearing strain. We know shearing strain is equal to delta x by L is equal to tan theta. So usually theta is a very small. This small angle approximation simplifies our calculations and helps us understand the behavior of materials under stress. So for small theta, we can approximate tan theta is approximately equal to theta. Therefore, shearing strain is equal to tan theta approximately equal to theta. Now, volume strain. So volume strain is the ratio of the change in volume to the original volume of solid. This concept is important because it helps us understand how materials respond to stress, particularly when they are subjected to uniform pressure. If we talk about the definition, so we can say volume strain defined as the ratio of the change in volume delta V to the original volume V. So it will be delta V upon V is equal to volume strain. Strain produced by a hydraulic pressure is called volume strain. This type of strain is significant in fields like engineering and material science, where understanding materials behavior under pressure is essential. Now, we are going to explore the concept of Hooke's law. So let's discuss uh, of in details about the Hooke's law. The force required, if we talk about the definition, so we can say the force required to stretch or compress an elastic object is directly proportional to the distance it is stretched or compressed from its original position, as long as it stays within its elastic limit. This means that if you double the distance, the force is needed also double. Look at figure Hooke's law, which helps visualize the relationship. This principle is important for designing everything from simple things to complex mechanical systems. So force is applied, displacement is x, then force is double, the displacement is 2x, as shown in the. So uh, mathematically F is equal to kx. All right. So F is equal to minus kx for the restoring, where F is the applied force and x is the displacement, extension or compression, and k is the spring constant, which represents the stiffness of the material. Now, fundamental law of elasticity states that for small deformation, stress and strain are proportional. This principle is essential because uh, it forms the basis of the understanding how materials deform under various forces. All right, and remember this proportionality holds true only within the elastic limit of the material. So, stress is directly proportional to strain. So, for removing proportionality constant, there is a constant. So, stress is equal to K into strain. K is the proportionality constant. While this law works for most materials, some materials don't follow this linear relationship. This deviation is significant when studying materials. They don't conform Hooke's law as it affects how we predict their behavior under stress. Summary. So let's discuss. First, solid maintains its shape size due to strong interparticle forces, showing elasticity or plasticity, permanent deformation. Spring ball model, which helps explain the elastic behavior of solids. Imagine atoms as balls connected by springs representing interatomic forces. This model shows how solids can return to their original shape after being deformed as the springs pull or ball back to place. We introduce the concept of stress, which is the restoring force per unit area. It's calculated as force divided by area and is measured in pascals. Stress helps us understand how much force a material can withstand before deforming. Three types of stress: longitudinal, shearing, and hydraulic. Strain measures deformation relative to original configuration. Three types of strain: longitudinal strain, shearing strain, or volume strain. Hooke's law states stress is proportional to strain for small deformation. So, students, practice questions are given here. So, try to solve these problems. So, first, a force of 200 Newton is applied perpendicularly to a surface of area 0.05 meter square. Calculate stress. What is the SI unit of the stress and what is its dimensional formula? Third, write the mathematical formula for stress. And fourth, how is the longitudinal strain mathematically expressed? A wire of original length 5 meter is stretched to a length of 5.005 meter. Calculate the longitudinal strain. Alright, so these are the practice questions and all are homework. Last one, a body experiences a stress of 3 into 10 raised to the power 7 Pascal. If its proportionality constant uh, K is equal to 6 into 10 raised to the power 5, 10 raised to the power 10 Pascal, calculate strain. Alright, thank you for your attention.